What specific problem does your proposed method of knowledge distillation aim to solve, particularly regarding the limitations of existing top K methods in LLMs?
Our proposed method of knowledge distillation, termed random sampling KD, aims to address two critical limitations of existing top K methods in LLMs: biased estimation of the teacher's probability distribution and the loss of tail information. Top K methods provide a biased estimator because they only retain the highest probability logits, which skews the distribution and leads to miscalibrated outputs. Additionally, these methods discard the tail of the distribution, which contains valuable information for rare tokens, resulting in a poor training signal compared to using the full distribution. By employing importance sampling, our method ensures an unbiased estimate of the teacher's distribution while preserving the gradient in expectation, thus maintaining model performance comparable to full distillation with significantly reduced storage requirements. This approach effectively mitigates the overconfidence issues observed in top K methods, leading to better calibrated student models.
How does the proposed random sampling knowledge distillation method work? Please outline the methodology step by step, including how it addresses the main issues identified with top K methods.
The proposed random sampling knowledge distillation (RSKD) method works by utilizing importance sampling to obtain unbiased estimates of the teacher's probability distribution. First, it samples tokens from a proposal distribution, which is designed to minimize variance while maintaining a similar number of unique tokens as the top K methods. This sampling process is repeated for a fixed number of rounds, and each sampled token is assigned a likelihood ratio to normalize the subsampled target probability distribution. RSKD addresses the main issues identified with top K methods by providing an unbiased estimate of the teacher's distribution, thus avoiding the bias and miscalibration that occurs when only the top probabilities are used. Additionally, it preserves the gradient in expectation compared to full distillation, ensuring that the student model learns effectively from the teacher's distribution without discarding valuable tail information. This results in improved model performance and calibration, as demonstrated through empirical analysis in the paper.
Can you provide a specific example of how the random sampling KD algorithm operates in practice, illustrating its steps with a hypothetical scenario involving token probabilities?
The random sampling KD algorithm operates by utilizing importance sampling to obtain unbiased estimates of the teacher's probability distribution. For instance, consider a scenario where a teacher model outputs a probability distribution over a vocabulary of 10,000 tokens, with the top token having a probability of 0.5, the second token 0.3, and the remaining tokens having lower probabilities. Instead of using just the top K tokens, random sampling KD samples tokens from the entire distribution, assigning each sampled token a likelihood ratio based on its original probability. If we sample 100 tokens over several rounds, the algorithm normalizes these sampled probabilities to create a subsampled target distribution that maintains the same average number of unique tokens as K. This process ensures that the student model receives a more accurate representation of the teacher's distribution, preserving the gradient in expectation and improving calibration, as demonstrated in the empirical results of the study.
What are the empirical advantages of your random sampling KD method over the top K and full KD approaches, particularly regarding model performance and calibration?
The random sampling KD method demonstrates several empirical advantages over both top K and full KD approaches. Firstly, it provides an unbiased estimate of the teacher's probability distribution, which is crucial for maintaining model performance. In contrast, top K methods yield a biased estimator that leads to miscalibrated outputs. Secondly, random sampling KD preserves the expected gradients at the logits, resulting in better alignment with full KD gradients, while top K methods exhibit significant discrepancies in gradient norms. Additionally, models trained with random sampling KD achieve superior calibration, mirroring the performance of full KD, while using only 62 unique tokens, which is a significant reduction compared to the large number required by top K methods. Finally, empirical results show that random sampling KD outperforms top K in speculative decoding acceptance rates and zero-shot NLU scores, indicating enhanced overall model performance.
Detail the validation process for your proposed method. What datasets, metrics, and experimental setups did you use to demonstrate its effectiveness compared to existing methods?
To validate our proposed random sampling KD method, we conducted experiments using multiple datasets and metrics. We trained llama-style student models, specifically a 6M parameter model using a 4B parameter teacher, across various token counts, including 68B tokens, to ensure robust evaluation. The effectiveness of our method was assessed through metrics such as language modeling loss, expected calibration error (ECE), and speculative decoding acceptance rates, which correlate with model performance. We compared our results against existing methods, including full KD and top KKD, and found that our method achieved comparable performance in language modeling tasks and better calibration, as evidenced by lower ECE scores. Additionally, we evaluated the models on downstream tasks, including zero-shot NLU and instruction-following tasks, demonstrating that our method consistently outperformed others across these evaluations.
What limitations or challenges did you encounter with your proposed random sampling KD method that may affect its generalizability or application in different contexts?
The proposed random sampling KD method faces several limitations that could impact its generalizability across different contexts. Firstly, while it provides unbiased estimates of the teacher's probability distribution, the method's performance is sensitive to the choice of sampling temperature, which can affect the variance of probability estimates and thus the model's calibration. Additionally, the method still requires a significant number of unique tokens, 62 tokens, to achieve performance comparable to full KD, which may not be feasible in all scenarios. Furthermore, when adapting the teacher model to different data distributions, the performance gains are contingent on the teacher being fine-tuned on the new data, which may not always be practical. Lastly, while the method improves pre-training scores, it can lead to higher calibration errors in downstream tasks, indicating a potential trade-off between pre-training performance and fine-tuning effectiveness.